Alright, in the previous lecture we have learned what is AVL tree. Now in this lecture we will talk about why we need AVL tree. To answer this question, let's look at this example over here. Let's say we have numbers like this and we want to insert them in binary search tree. So if I try to insert them one by one, as you would have guessed, our tree will be like this. So first I'm inserting 10, so the 10 will be the root node in this case. Then I'm going to insert 20. So in this case we are going to compare 10 with 20. We see that 20 is greater than 10. This means that it's going to be added as a right child over here. Now after adding 20, I'm going to add 30. So if I add 30 over here, you'll see that first it's going to compare with 10. We see that it's greater than, so this means that we need to add this 30 to the right child. So we are coming to 20, so we see that it's greater than 20. So this means that it's going to be added as a right child over here. Now if I continue adding all these numbers over here, at the end our binary search tree will look like this. So here you can easily see that all nodes are added as a right child over here. So this is how our binary search tree will look like after adding all these numbers over here. So here everything is clear, we don't have any problem. Now here the problem is if I want to search, for example, for the node of 60, we will start from the root node and we will keep traversing until we find the 60 over here. Now here, if we look at the number of nodes that we have visited, we can easily see that we have visited 6 nodes to find the 60 over here, which is almost all nodes, because in this case we have 7 nodes in our binary search tree. Here we have visited 6 of them. So this means that to find 60 over here, the time complexity is ON. And we know that in case of binary search tree, the time complexity for searching an element is O log n. So what happens over here? So this is because the height of tree is too much. So let's say if the same tree over here is more balanced, then in this case our binary search tree will look like this. So we have same numbers over here. In this case this binary search tree is balanced. So this means that if I search for 60 over here one more time, it will take O log n time complexity, because in this case we have visited only to the right child, and in the right child we have straight away found the 60 over here. So this means that if the binary search tree is not balanced, in this case the time complexity for searching element will be ON. Now from these two trees over here, you can easily see that there is a difference between the performance of searching in these two trees over here. Similarly, when we delete and insert elements to this first tree over here, we will face the performance issue over here. So it's obvious that the performance issue was because of the height of the tree, and this is because of the disbalance of the nodes in this first binary search tree over here. Now the main question is how AVL tree helps us in this case. So AVL trees make sure that we never end up this kind of disbalanced tree over here when we are inserting nodes to the binary search tree. AVL trees enforce some rules when we are inserting or deleting nodes from binary search tree to make sure that the tree will never be disbalanced. Because of that, our tree will always be balanced, so we will not have performance issue like we had over here. So as we mentioned, AVL trees solve the problem of disbalancing by using rotation. So every time when tree is disbalanced, AVL tree performs some rotations to get the tree balanced again. Now what is the rotation and how is it done? We will answer these questions in our upcoming lectures. So whenever we are inserting or deleting the elements from the binary search tree, if the binary search tree becomes disbalanced, in this case we are going to perform rotations and we will make our binary search tree balanced. So with this we are going to prevent the performance issue that might happen after insertion or deletion of elements in binary search tree. So this is the main reason why we need an AVL tree. So hopefully everything is clear about this lecture. So in this lecture I have explained you why we need an AVL tree. So see you in the next lecture.